This is information hierarchies with Ben Brooks and Emir Kamenitsa, my colleagues at the University of Chicago. This paper essentially looks at relationships between different notions of what we might mean when we talk about one person knowing more than another person. So what does it mean when we say that Anne knows more than Bob? So to fix ideas, suppose there's an uncertain state of the world, omega. We have a common prior on the state, and then Anne and Bob are each going to observe a signal of the state. So let's think about different ways we might partially order Anne and Bob's information. One obvious way we might do this to talk about Anne knowing more than Bob is using the Blackwell order. So we would say that Anne's information is more accurate than Bob's in the sense of Blackwell if the distribution of Anne's posterior beliefs is a mean-preserving spread of the distribution of Bob's posteriors. And as we know, this captures the decision theoretic notion that Anne's information is going to be more valuable for any decision problem that they might face. So this is one thing we might mean to say that Anne's information, or that Anne knows more than Bob. Another stronger thing we might mean when we say that Anne knows more than Bob is that Anne actually gets to see what Bob sees, plus something else, plus an additional signal. We're going to call that the refinement order on signals, because if we model signals using a partition, this corresponds to Anne's signal being a finer partition of the space than Bob's signal. And so you see that if you have signals that are refinement ordered, this is stronger than the Blackwell order. For instance, Anne doesn't just have more dispersed beliefs, she actually knows Bob's posterior belief in addition to her own. So as we all know, the refinement order implies the Blackwell order. So if signals are refinement ordered, then belief distributions are Blackwell ordered. The reverse does not hold, but there's something that we might call a partial converse or a partial equivalence. If I tell you that Anne's information is more accurate than Bob's, and so Anne's distribution of posteriors as Blackwell dominates Bob's distribution, we can always look at those distributions and find refinement ordered signals that induce those posteriors. So refinement implies Blackwell, and Blackwell is always compatible with refinement. So there's this partial equivalence. What we do in this paper is to think about the connection between these two notions of more information when we add agents. So now instead of just Anne and Bob, let's add Charlie and David. Suppose that Anne has more information than Bob and Charlie have in the sense of, more accurate information in the sense of Blackwell. And then Bob and Charlie each have more accurate information than David, as indicated by this little network diagram here. So if I specify certain belief distributions satisfying those conditions, we can ask the question, is it necessarily possible that these belief distributions are compatible with the refinement order, that Anne can actually see what Bob and Charlie see, and Bob and Charlie see what David sees? The answer we're going to give is no. It's not necessarily going to be the case, so we're going to have a counterexample that shows that this isn't possible, and we're going to explore conditions on the network structure under which we can or cannot come up with such counterexamples. Before I get into the details, let me just give a couple motivating applications of the kinds of questions you can ask with what we do, ask and hopefully answer. First, think about a problem of rationalizing the reactions to unknown sources of information. So suppose Anne obtains information from some set of information sources or experiments. Let's call them X, Y, and Z. And so Anne might observe experiment X, she might observe experiment Y, she might observe experiments X and Y, some subset of these experiments. So think of the following exercise for an econometrician. The econometrician gets to observe Anne's reaction, her distribution of posterior beliefs, at every subset of these experiments. So the distribution of beliefs if Anne observes just experiment X, just experiments X and Z, X, Y, and Z, and so forth. The question is, can these reactions be rationalized as Bayesian responses to some experiments? There's two clear necessary conditions for rationalizability. The first is what's often called Bayes plausibility in the literature, that the average posterior belief has to be the same across any subset of experiments she sees. The average posterior is always equal to the prior. And another condition is Blackwell monotonicity, that if Anne sees more experiments, her posterior beliefs should be a mean preserving spread. So if you observe experiments X and Y, your posteriors are more dispersed than if you just observe experiment X or just observe experiment Y. So you can ask, are these conditions necessary and sufficient? And we're going to show in the paper that the answer is no. So other conditions are necessary. And we don't actually have a full characterization of those. We think it's an interesting open question going forward. Another application of the kind of the exercise we're doing is to think about information design, but specifically think about information design with monotonicity constraints. So there's a designer who's going to provide private signals to multiple receivers under the constraint that some receivers must have access to other receivers' information. So think about an organizational hierarchy. I'm trying to provide information to both a boss and a subordinate, but I face the constraint that any information I provide to the subordinate must also be observable by the boss. The boss has access to whatever the subordinate sees. You have similar kinds of monotonicity constraints that might arise in games of coalition formation. So imagine that a set of agents are going to merge into different kinds of coalitions, and I would like to give information to the agents so that coalitions know something when they get together. Well, clearly larger coalitions have to know more than smaller coalitions. If Anne, Bob, and Charlie all get together, they definitely know anything that just Anne and Bob know on their own. We might also get some similar kinds of constraints if you're thinking about a dynamic revelation problem. Me in the future has to know everything that me in the past has learned. And so when you're thinking about an information design problem with this sort of constraint, we're going to show that sometimes it'll be the case that all information structures consistent with the Blackwell order are possible. Other times they're not all possible and there will be additional constraints, and it's going to depend on the network structure of the monotonicity constraints, as I'll describe. All right, so let me go into the model now. There's a finite state space capital omega with typical state little omega, and we're going to learn about the state through experiments or signals. So let me give you a little bit of notation here. It's not super important that you follow it all, but this is just a general framework for putting the set of all possible signals into a common probability space. So we can think about, what's the correlation between different signals? What happens if I observe signal A and B, and so forth. So we're going to model a signal, little pi, and the set of all signals, capital Pi, as a partition of the state space omega across the unit interval 0, 1. So a signal realization is then going to be an element of this partition. So it's going to be a subset of the state space across the unit interval. And the way a signal realization gets realized is as follows. Think about drawing the state omega and then also drawing a uniform auxiliary variable x, uniformly drawn from the interval 0, 1. And then given a signal pi, the realization we observe is the partition element that contains omega x. So what this means is if I tell you a signal, the signal contains the information about all of the likelihoods of each signal realization in every state. And it also contains all the information about its correlation with other signals. With this notation in hand, we can now introduce the refinement partial order on signals. Signal pi refines pi prime, which we indicate with the triangle greater than equals. If pi is a finer partition, meaning that every element of pi is a subset of some element of pi prime. And this exactly captures the idea that Anne gets to see Bob's signal plus some extra information. So if my signal is a refinement of yours, I know your signal realization, plus maybe something else. And we can also look at what happens if I get to observe two signals, pi and pi prime. Again, because we have this partitional structure, the new signal that corresponds to observing these two signals is just going to be the join of the two. So pi join pi prime, the coarsest partition finer than both signals. Now let's move to distributions of beliefs. So denote a typical distribution of beliefs by tau, where once we specify a prior mu naught, any distribution of beliefs has to satisfy the expectation equal to the prior. We have the Blackwell partial order on distributions of beliefs. Tau Blackwell dominates tau prime, indicated by the squiggly greater than equals, if tau is a mean preserving spread of tau prime. Any signal pi induces some distribution of beliefs that I'll denote by braces pi, and refinement order signals imply Blackwell ordered induced belief distributions, which in our notation we would write as pi refines pi prime with the triangle equals, implies braces pi, Blackwell dominates braces pi prime. All right, the title of the paper is Information Hierarchies. Here are what information hierarchies are. An information hierarchy H is just a finite partially ordered set. So we have a set of nodes N and a partial order greater than equals on the set. Given some information hierarchy, we can draw a graph of the hierarchy, a directed graph in the following way. Draw an edge from node N to node N prime if N covers N prime, meaning that N is above N prime, and also there's nothing in between. So in the graph of Anne, Bob, Charles, and David we saw before, Anne is above Bob, so we draw an edge from Anne to Bob. Bob is above David, so we draw an edge from Bob to David. Now Anne is also above David, but we don't draw an edge there because it's implied by transitivity. Anne above Bob, Anne above Bob, Bob above David. So that's the directed graph of an information hierarchy. And we can also look at the undirected graph of the hierarchy just by erasing the arrows. And then we have just a graph where we have a little loop, Anne connected to Bob, Bob connected to David, David connected to Charles, Charles connected to Anne. Let's now put our beliefs and signals onto this information hierarchy. So a belief allocation beta is going to be a map from nodes to belief distributions. A signal allocation sigma is going to be a map from nodes to signals. And then any signal allocation induces a belief allocation node by node. We just look at what's the signal provided to each node, and that induces a belief distribution at that node. We say that a belief allocation is monotone, again, with respect to the underlying hierarchy, if higher nodes have Blackwell more informative belief distributions. And we say that a signal allocation is monotone if higher nodes are allocated signals that refine the signals provided to lower nodes. It's true that any monotone signal allocation induces a monotone belief allocation. Again, this is just restating the observation I made before, that refinement ordered signals imply Blackwell ordered induced beliefs. We're going to flip that question around and ask the reverse question. Given some monotone belief allocation, does there or does there not exist a monotone signal allocation that induces it? So stating this question a little bit more formally with a little bit more notation, fix some hierarchy, some state space, and some prior. We say that a monotone belief allocation beta is constructible if there exists a monotone signal allocation sigma that induces it. A hierarchy is omega universally constructible for some state space omega if for all priors every monotone belief allocation is constructible. And then the hierarchy H is universally constructible without the omega qualifier if it's omega universally constructible for all possible state spaces. The question we're going to ask in this paper is which hierarchies are universally constructible? A couple small notes. First, our results about universal constructibility do not depend in any way on the priors. That's a bit of a red herring. If you are constructible for all the belief allocations on one prior, then you're constructible for all the belief allocations at another prior. So that's not an important thing. It turns out that the state space is important. In particular, the cardinality of the state space can matter. It might be the case that you're universally constructible for small state spaces, but not for large state spaces. And so that's why we have this kind of separation of the omega universal constructibility before looking at full universal constructibility on all state spaces. All right, so let's now go through examples. I'll first present a few very simple examples of information hierarchies, and then I'll walk more slowly through the constructibility or the non-constructibility of each one.
Alex, can I ask a question?
Yeah.
So is it important though that there's a common prior? Meaning that all agents have the same prior?
I think it's probably not important except for, well, so I guess there's, right. So we couldn't really define the Blackwell order on belief distributions without a common prior. I guess we could still define the Blackwell order on kind of the underlying experiments. So I think it shouldn't be important that there's a common prior, but I'll have to think about that more. Definitely, like, we rely on it pretty heavily notationally, just because we're kind of working with belief distributions. And I'd have to think more about whether we can kind of fully generalize to none without common prior. Thank you.
Okay.
All right. Okay, so first, just going through examples of information hierarchies. Remember, information hierarchies are just partially ordered sets that I'm graphing in a particular way. So here is a chain information hierarchy. A is above B, is above C, is above D. We can also have a tree information hierarchy where you have a president in charge of 2 division managers, and then the division managers are each in charge of 2 assistants. Here we have the diamond information hierarchy. That's Anne, Bob, Charlie, and David from before, where Anne is the president. She's in charge of division managers Bob and Charlie, and then Bob and Charlie both share the same assistant, David. And again, just as a reminder, we don't draw the arrow from Anne to David, even though Anne is above David. It's implied by transitivity. Here is the crown information hierarchy on the left. You have a father and a mother who are both above a son and a daughter. And then on the right, we have the cross hierarchy, which is what you get when the family on the left hires a governess to watch over the children. So now you have a father and mother above a governess, and the governess is above the son and the daughter. And one thing I want to flag here, just to observe, is that here we've added a node to the information hierarchy, and in so doing, we've removed some edges. We no longer draw the edge from father to son, because with the governess in the picture, father is above governess, governess is above son, so we don't need the arrow from F to S anymore. All right. Let's now go through the universal constructibility, or lack thereof, of each of these examples. Let's start with the simplest one, which is the chain. The chain is universally constructible, and there really isn't anything surprising here. This construction is going to be kind of very standard, somewhat familiar, but let's just walk through it to see how we actually get there. So in order to show that the chain is universally constructible, what I need to do is I need to take an arbitrary monotone belief allocation beta on this hierarchy. So some belief distribution at A, B, C, and D, where higher nodes are Blackwell dominate lower nodes. And then we seek to find a monotone signal allocation where the signals induce the appropriate belief distributions and also satisfy the refinement order with higher nodes having refinements of lower nodes. We're going to do this just by starting at the bottom and working our way up. So take any old signal, sigma of D, that induces the belief distribution at the bottom, beta of D. And it's a very standard result that for any belief distribution at C that's Blackwell more informative than this one, there exists some signal that refines the signal provided to D that induces the belief at C. Essentially, all I need to do is I take the signal at D, I can then refine it to get some appropriate signal at C that induces the correct belief distribution. I can then refine that one to get a signal at B that induces the correct belief distribution. I can then refine that one to get the signal at A. And so chains are universally constructible. That one is easy to handle. Now let's move to the tree. The tree is also universally constructible, but I can't quite use the same argument as I just used because I can't just hit all of the nodes only by going up. I might also need to go down. So think about starting with some signal allocated to assistant 1. We can refine that to get a signal for D1. We can refine that to get a signal for P, but we can't go up anymore. To fill out the rest of the tree, we need to go down from D1 to A2, go down from P to D2, and so forth. This isn't as easy as going up. For instance, if we have some signal at D1 that induces the appropriate belief, it is not true that that signal can necessarily be coarsened into a signal that induces the correct belief distribution for A2. That's just not the case. So we can't just coarsen to go down. What we're going to do instead is show how we can go down, not by coarsening the signal we already have, but by reassigning the signal, changing the signal that's been previously assigned around so that it can be coarsened. So when we want to, let's say we start at A1, we refine to D1, we refine to P, and we now want to go down from D1 to A2, we show in the paper how we can reassign the signals at D1 and P so that now D1 can be coarsened into A2 and the belief distributions at D1 and P haven't changed. With this result in hand, now we can fill out the whole tree just by node, adding one at a time, either going up or going down. So start at A1, go up to D1 by refining, reassign and coarsen to go down to A2, refine to go up to P, reassign and coarsen to go down to D2, and so forth. So the tree is universally constructible using this approach. Thinking back to the cross hierarchy, that one is also a different shape of tree when we're thinking about the graph as a network. So the cross is also universally constructible by exactly the same argument. Now let's go to the diamond. The diamond is not universally constructible. And so what I'm going to do here is I'm going to present a counterexample where I'll give you a belief distribution, a belief allocation, beta, where I assign a belief distribution to each node, where those belief distributions are consistent with the Blackwell order, but I'm going to show you that there are no signals that induce these belief distributions that are consistent with the refinement order on this hierarchy. And so let me walk through this example somewhat slowly. Take the state space to be binary, 0, 1. So any belief is just a point on the 0, 1 interval. Assign to node D the beliefs 50-50 at 1/6 or 5/6. At C, assign 3/8 probability to 0, 1/8 probability to 2/3, 1/2 probability to 5/6. At B, we just do the reverse of that, just flip it over 1/2. And at A, we have 3/8 at 0, 1/4 at a half, and 3/8 at 1. So I won't walk through this, but it is easy to see that these beliefs are in fact mean preserving spreads. A is a mean preserving spread of B and C each a mean preserving spread of D. And so now let me argue that there is no signal allocation that's consistent with refinement that induces these belief distributions. And the key observation is that refinement implies that beliefs are going to be a martingale as we move up the chain, that they preserve expectations. So if your belief is 1/6 at D, and you're trying to think what are the possible beliefs that person B has, well, my expectation of B's beliefs must be 1/6. If my belief at D is 5/6, my expectation of B's belief must be 5/6. That's implied by the refinement order. And so if my belief at D is 1/6, the only way that that can be consistent with this martingale property is for B also to have belief exactly 1/6. Because there's no way of spreading out the belief of 1/6 any other way to get the belief distribution at B. Because if any beliefs are going to the right, then some beliefs must also go to the left, but there's no room on the left to split things out. So if D's belief is 1/6, then B's belief has to be 1/6 as well. And if B's belief is 1/6, then A's belief has to be 0 or a half, but cannot be 1. Why not? Well, all of the probability mass of A's belief at being 1 has to come from B's belief being 1. Because if B's belief is 1, then A's belief is definitely 1. So A's belief of 1 isn't getting any probability from B's belief of 1/6. So just to say that again, if D's belief is 1/6, and we satisfy the refinement order on signals, then B's belief is 1/6, then A's belief has support 0 and a half, but not 1. Now let's think about going from D to A through the other path, through C. If D's belief is 1/6, then C's belief is either 0 or 2/3. And if C's belief is 2/3, then A's belief has to have some probability on being 1, because if we're splitting the 2/3, it's got to go somewhere to the right. And the only way to go to the right is 1. So from the D to C to A path, D's belief of 1/6 has a positive probability of A's belief being 1. So this is a contradiction. Conditional on D's belief being 1/6, I've argued both that A's belief has a 0 probability of being 1 and a positive probability of being 1. This shows that no signals can be consistent with the refinement order and induce this belief distribution. Let's move now to the crown. The crown is also not universally constructible. It turns out that there's no counterexample to constructibility with only binary state space. You actually need a minimum of 3 states in order to give such a counterexample. I'm not going to walk through this the way I did the other one, but the picture is here if you want to take a look at it. We assign beliefs to FM, S, and D on this now this triangle that represents the space of beliefs on 0, 1, 2 in the following way, with the letter indicating that this circle is in the support, or the point at that circle is in the support of your beliefs. And we can give a similar argument where we show that conditional on some belief at S, going to the S to F to D path gives inconsistent conditional beliefs as if we went the S to M to D path. So the crown is also not universally constructible. All right, now let me present the main theorem of the paper. An information hierarchy is universally constructible if and only if its undirected graph is a forest, meaning that there's no cycles in the undirected graph. So just going over the examples we saw before, the chain, the tree, the cross are universally constructible, no cycles. The diamond and the crown are not universally constructible. When we erase the arrows, we get cycles. And just as a reminder, we got from the crown to the cross just by adding a node. So we were able to add a node, and we went from being not universally constructible to being universally constructible. To show this theorem, we need to show it in the two directions of the if and the only if. The if direction we've essentially already argued for informally. I showed you that the tree is universally constructible, and a forest is just a disjoint union of trees. So the exact same argument shows that an information hierarchy is universally constructible if its undirected graph is a forest. The other direction is going to be the hard direction. We want to show that if the undirected graph is not a forest, so the undirected graph has a cycle, then we are not universally constructible. The details get pretty complicated, but on the very, very high level, essentially what we're doing is we're showing that in any graph that has a cycle, we can embed a version of either the diamond counterexample or the crown counterexample. And so with those two kind of building blocks, we can then show that any other graph with a cycle is also not constructible. So that gives a connection between the refinement order on signals and the Blackwell order on belief distributions. In the paper, we actually have a bit of a generalization of that. We think about other meanings of what it means for Anne to know more than Bob that are in between refinement and Blackwell. So here's another thing that's not quite as strong as refinement, where I'd also certainly be comfortable saying that Anne knows more than Bob. Suppose that Bob's signal is statistically redundant with Anne's. So Anne's belief doesn't change if she observes Bob's signal. This is exactly what you'd get if Bob observes a garbling of Anne's signal. So that does not imply refinement, but it is another way in which Anne might know more than Bob. A different notion might be that Anne doesn't know Bob's full signal realization, but Anne knows enough to know Bob's first order belief about the state. And then Bob also observes some irrelevant other information that I don't know. Both of these notions of Anne knowing more than Bob continue to imply the martingale property on beliefs, that Bob's expectation of Anne's belief is equal to Bob's belief. And it turns out that's really the only property we needed for these counterexamples. And so in the paper, you'll find the following, this version of the theorem. We say that a relation on signals is proper if it's implied by the refinement order and it implies the martingale property on beliefs, which in turn implies the Blackwell order on induced belief distributions. And for any proper relation R, which now might mean refinement, it might mean statistical redundancy, it might mean knowledge of first order beliefs, what have you, an information hierarchy is universally constructible under that relation if and only if its undirected graph is a forest, meaning that if the graph is a forest, then for any belief allocation that's monotone in the Blackwell order, we can find a signal allocation that's monotone with respect to this relation that induces it. And if the graph is not a forest, then there exist counterexamples. Just to finish up, let's go back to this question I posed at the beginning about rationalizing reactions to unknown information sources. So Anne has access to a set of experiments. The econometrician has a data set that gives us Anne's belief distribution at every subset of experiments. And we ask the question, when is a data set rationalizable? Well, tying this back to the results I presented, we can graph the following information hierarchy to represent the connection between Anne's beliefs at different observations of subsets of experiments. If Anne observes experiment X and Y, then her then her signal must be a refinement of what she knows just observing X or just observing Y. If she observes X, Y, and Z, her signal is a refinement of what she observes just observing X and Y, just observing X and Z, and so forth. So Anne's signal allocation must be a refinement monotone if these reactions are rationalizable. And as we just argued, Blackwell monotonicity is not sufficient to imply consistency with refinement monotonicity. And so therefore we know that we need additional conditions for rationalizability. And this we consider to be an open question. We don't know what the full characterization is. We just know that Bayes plausibility and Blackwell monotonicity is not enough. All right, so to finish off, there are a couple kind of open questions that we think this analysis raises. The first one, the big question, is essentially the rationalizability one I just mentioned. Fix some arbitrary information hierarchy that's not a forest. We know there exist non-constructible belief allocations. We don't know how to generally determine whether a given belief allocation is constructible or not. We view that as kind of a big open question. And then there's also a smaller, more technical open question, which is thinking about binary state spaces. So for binary state spaces, remember, the diamond is not universally constructible, but the crown hierarchy is universally constructible on binary state spaces. We needed 3 states or more to find a counterexample. So we don't have a full characterization of universal constructibility on binary state spaces. We think that's kind of an interesting question as well, though considerably smaller than the big question. That's all I got. That's it.
Thank you, Alex. So we do have some time for questions or comments if there are any.
I do. I have a question.
Great.
What remains of the theory if instead of the interval 0, 1, you get only a finite set?
But it's a, so if we're changing our signaling technology, is that the question?
Yes. So instead of having a continuous variable, you have only finitely many signals.
As long as it's, so we've made a bunch of finiteness assumptions just for technical ease here. So we're thinking about belief distributions that have finite support. And so from that perspective, as long as you have sufficiently many finite realizations on your signaling space, then there's no problem. If we're thinking about a case where this constraint actually binds, where we kind of no longer have access to the full set of signals, I guess that would mean that we don't necessarily have, we're not necessarily going to be able, even in the chain, to, refine, have Anne more informed than Bob in a refinement sense, if we don't have a kind of flexible enough signaling technology to actually refine Bob's signal into Anne's belief distribution.
I see. So when you say sufficiently large set of signals, you refer, it depends on the size of omega, I guess, right? Or no, or what?
The size of omega, and also it's going to depend on, I guess, the belief distributions in question. How, if the belief distribution has support on a lot of possible beliefs, we need a signaling space that has support on at least as many beliefs as the support of the belief distribution.
Okay, got it. Thank you.
Alex, I have a question. So in the construction for the tree, you were sort of alluding to having to sort of go up and down.
Yeah.
And I was wondering, for the tree, why couldn't you just go down? You know, start at the top, and then the black hole comparison and beliefs is going to imply that you can find a refinement.
Good.
And then just do that iteratively, sort of along every branch.
So 2 responses to that. The first one is that you would have to choose the right signal. You can't choose an arbitrary signal at the top node that happens to induce the belief distribution. That one isn't necessarily going to be able to be coarsened into the lower ones. You'd have to kind of choose the right one. You'd have to choose as kind of a refinable one. Now, it might be possible to kind of look at everything we're going to need up front and then find such a signal. But where that's really going to fail is, let's look at the cross hierarchy now. Even if we could kind of generalize such an approach that happens to work when there's one root node and everything kind of below that, it's not going to work for the cross hierarchy. So we still need to kind of put in the work to figure out this reassignment procedure to be more general.
Thanks. Okay.
All right, thank you.
Thank you very much.